Welcome to the second video of our Math and Python programming series, where we'll explore exam problems related to functions, derivatives, and integrals. In the previous video, we tackled combinatorics problems, and our approach was to simply guess the answers. However, in this video, we won't rely on guesswork at all. Our main focus will be on functions, their derivatives, and integrals, using Python code. The objective of this video is to understand derivatives and integrals by letting the computer handle all the complicated mathematical calculations. Instead, we'll concentrate on the key concepts and important aspects of the problems. To achieve this, we'll leverage the power of Python and use the SymPy library, which will take care of all the tedious calculations. This way, you can devote your attention to the exciting and essential steps of the mathematical problems without worrying about memorizing numerous formulas and algorithms. So let's dive in and explore the fascinating world of derivatives and integrals with the help of Python and SymPy. In this video, just like in the one where we discussed Python and combinatorics, we'll tackle 4 final exam problems that involve understanding derivatives and integrals of functions. These concepts are essential for analyzing functions in mathematics. My main aim is to help students who are preparing for exams, especially those considering an engineering specialty. Additionally, professional programmers can benefit from this video by refreshing their knowledge of certain mathematical aspects and getting acquainted with the fantastic Python library called SymPy. I want to emphasize that all the code demonstrated here is freely available, and you can find the relevant Colab document link below this video. I encourage you to play around with the code on your own to fully grasp the ideas presented in the video. Give a man a fish, and you feed him for a day. Teach a man to fish, and you feed him for a lifetime. In the context of our video, we can adapt it as follows. While watching YouTube for a year might offer some insights, programming with Python for even just a day can pave the way to securing a job. Let's begin with the first task, which consists of 4 parts. The initial part is the easiest, where we need to find the derivative of a given function. To help us with all the problems, we'll be using the SymPy library. As you might have guessed from its name, SymPy is a Python math library that goes beyond just providing numerical answers. It specializes in handling mathematical expressions and enables us to perform symbolic math calculations. To better grasp this concept, let's take a look at the code. As always, we start by importing the SymPy library. Next, there's an interesting step. We declare our own symbolic variable, x, which will be used for various mathematical manipulations. This lets the system know that x is the variable we'll work with in our math functions. Below that, we define our function. Please note that double asterisks represent the exponentiation operation. Finally, we instruct the system to find the derivative. The derivative is then stored in the variable y prime. To visualize the derivative expression, we print the value of y prime to the terminal. By following these steps, we can efficiently explore derivatives and gain a deeper understanding of mathematical expressions through code. As we delve deeper into this example, we encounter a fascinating aspect of math that not every programmer may be aware of: symbolic calculations. Now let's take things a step further and explore this intriguing concept by connecting to the Google Colab system and running our program right from a web browser. To do that, simply click on the link provided below this video to open the Google Colab notebook. Once there, hit the Run All option to ensure that all the code for our math problems works perfectly. Each math problem is like a separate chapter in this notebook, and you can easily navigate through the content by clicking the Content Preview icon. Moving on to the second part of the problem, it challenges us to determine the values of x, where the function fx decreases. To solve this, we need to recall a valuable fact. The function's values decrease where the derivative is negative. Thanks to the power of SymPy, we can solve this problem with just a single line of code. It's amazing how quickly and efficiently we can tackle such mathematical challenges using Python. So let's continue this exciting journey and see what wonders we can unravel with the help of SymPy and our coding skills. Let's dive into another exciting feature of SymPy, the solve function. With this function, we can instruct SymPy to solve inequalities, like finding where the derivative is less than 0. The magic happens instantly. We obtain the answer, revealing two intervals, when x ranges from -infinity to -1, and when x ranges from 3 to infinity. But wait, there's more. SymPy has an awesome method called plot implicit that visually represents the solution of our inequality. This graphical representation helps us better understand the solution. Moreover, we can go a step further and visually confirm the connection between our function and its derivative. By drawing both on a graph, we can clearly see how the derivative is indeed negative in the regions where the function decreases. Now let's move on to the third part of our problem. This time, we'll explore how to perform integral calculations using the SymPy library. Our task is to calculate the area between the tangent of the function at the point where ax equals 3 and the function itself. Exciting stuff, isn't it? With SymPy, we can explore math concepts in a whole new light, making learning more engaging and insightful. Let's take the first step and calculate the value of the function at x equal to 3. Simultaneously, we'll find the derivative at this point, which gives us the coefficient m for the tangent direction. Interestingly, we observe that m is 0, indicating that the tangent is parallel to the x-axis. Now we proceed to calculate the parameter b for the tangent equation by substituting the coordinates of the point of contact into the equation. Remarkably, b turns out to be 31. With both m and b in hand, we can write the tangent equation itself, which simplifies to y equals sine 31. The area we're interested in lies between the tangent and the original function. To facilitate this, we create a new function by subtracting the function's equation from the tangent equation. To find the desired area, we integrate the newly created function over the interval from 0 to 3. The result comes out to be 33 3/4. We proudly display the answer in the terminal. Congratulations! At this point, we've successfully grasped the essential elements of SymPy. The next 3 tasks will only reinforce this knowledge, as we know that repetition is the key to mastering any skill. So, let's keep up the great work and continue our SymPy journey with confidence. Welcome to the second task, where we'll be dealing with a fascinating challenge involving a parabola and a rectangle inscribed inside it. We are given 3 points on the parabola, and our first goal is to find the equation that describes the parabola's shape. To accomplish this, we start by writing equations for each of the 3 points, plugging in their coordinates for x and y. This gives us a system of 3 equations, which we can solve to find the coefficients of the parabola's equation. Now let's bring Python into the mix. We'll use it to help us handle the calculations efficiently. We'll define our symbols to represent the coefficients of the parabola's equation, and then proceed to create the system of equations. With the help of SymPy's solve method, we'll find the coefficients and obtain the expression of the parabola. Moving on to the second question of this task, we need to determine the expression for the area of the rectangle inscribed within the parabola. This area is influenced by the parameter a, which represents the distance from the origin of the coordinates to the rectangle. Here comes the interesting part. While Python can assist us in understanding the area expression, we'll need to exercise our creativity to come up with the expression ourselves. Let's put our thinking caps on and explore how this area can be represented mathematically. This task promises exciting challenges, but with our problem-solving skills and the power of Python and SymPy, we are well equipped to tackle it. Let's dive into the next part of this task. To begin, we'll declare the symbol A in SymPy expressions. The area of the rectangle is simply the product of its width and height. Now, how do we find the width? By considering the coordinates of point E, which is equal to 6, and then subtracting 2 distances A. Remember, A represents the distance from the origin of the coordinates to the rectangle. The height, on the other hand, can be obtained by inserting the A parameter into the parabola expression. Here comes the exciting part. SimPy offers two powerful methods to simplify mathematical expressions: simplify and expand. These will come in handy as we proceed. Now, moving on to the third question of this task. We want to find the value of A that maximizes the area of the rectangle. Whenever we're asked to find the largest or smallest value, we know that we need to look for a derivative. Lucky for us, we're already familiar with how to do this using the SimPy library. So, with our SimPy skills and a dash of mathematical intuition, we're well prepared to conquer this challenge. Let's continue exploring and uncover the mysteries that SimPy has in store for us. Firstly, we declare the symbol A for the SimPy package, as it will be essential for our calculations. Next, we create a list to record the values of the variation edges of the parameter A interval. For our specific case, the values are 0 and 3. Now, we recall our area formula, which we derived in the previous problem solution. To find the maximum value, we calculate the derivative of the area expression. This will help us identify critical points. Since our task is to find the maximum value, we set the derivative equal to 0 and solve the equation using SimPy's handy solve function. SimPy will provide us with two solutions, but we're interested in the one that falls within our interval between 0 and 3. This value will be our answer. Now, in a more general scenario, we would add the values of our variable interval to the list of extreme points. Then, we would check each point from this list and select the one that gives the highest function value. However, in our current case, this additional step is unnecessary as we already have the solution. So, with SimPy's powerful tools and a pinch of mathematical curiosity, we're well prepared to tackle complex challenges and find the maximum value with ease. Let's continue exploring the wonders of SimPy and unlock even more fascinating mysteries in the world of mathematics. Now, let's tackle the fourth question of this task, which aims to test our understanding of integrals. We need to find the area of the figure bounded by our parabola within the interval from 2 to 5. Believe it or not, the solution is remarkably straightforward. Just one line of code does the trick. Thanks to the SimPy library, we can effortlessly calculate this area, making the task a breeze. Integrals might sound complex, but with SimPy's help, we can easily explore and comprehend these mathematical concepts. So let's embrace the power of SimPy and confidently solve this question in a snap. Welcome to the third task, which bears a striking resemblance to the first one and consists of 4 parts. In the Google Colab notebook, you'll find Python solutions for all parts using the powerful SimPy library. Now let's focus on the fourth question, where we'll explore some exciting new elements of the SimPy library. Our task involves a given function, and we need to find the value of parameter A for which equality holds true. The left side of the equation contains an integral with the parameter A, while the right side involves the function itself with the parameter A. While this may seem like a daunting challenge, fear not. With SimPy's help, the solution is surprisingly simple. I'll present 2 solutions, and the second one will showcase the new capabilities of the Colab system. By the end of this task, you'll be amazed by the versatility and ease with which SimPy handles even complex mathematical problems. So, let's dive in and discover the wonders of SimPy and the Colab system. Now, for the first solution, we'll use the functions we already know. First, we declare the variable x and the function f. Additionally, we declare the symbol a. Next, we find the integral of function f over the interval from -1 to a. This integral results in a new function, where the variable is a. We'll store this function in variable f1a. To construct f2, we create a function that corresponds to the right side of our equation. With f1a and f2a in place, we then form f3 by subtracting f2a from f1a. Solving the equation f3 equals 0, we obtain three solutions. We choose the first solution, while the other two are complex numbers. The concept of complex numbers may not be typically taught in school, but I can mention that the letter I in the answer represents the square root of -1. Now let's explore another fascinating solution that showcases the capabilities of the Google Colab system. We'll call it a mathematical microscope. The idea behind this method is familiar to students. We plot two graphs, one for the function written on the left side of the equation and the other for the function written on the right side. The points where these graphs intersect represent solutions to the equation. We will create a function to draw the graphs. It is important to note that this function has two parameters, a1 and a2, which define the range of the function variable. To add even more intrigue, we'll explore how to make our graphs interactive in Colab system documents. The second code snippet demonstrates this fascinating capability. Now let's run the program and witness the magic in action. With the IPyWidgets module, we unlock the power of interactive graphs. Upon program completion, we not only have our graphs, but we also unveil two interactive elements, a1 and a2. By adjusting these elements, we can dynamically change the abscissa interval of the graph. It's like peering through a microscope, observing how the function behaves under smaller intervals. Intriguingly, we discover that the functions intersect at the value of a equal to 0. Now let's delve into the fourth and final problem to put our SimPy skills to the ultimate test. The function given to us is x raised to the 5th power. Additionally, we have a line passing through the origin that intersects this function. You need to find the area of the s figure between the line and the function. Furthermore, we'll compare this figure's area to that of the rectangle. Luckily, SimPy comes to our aid once again, making the solution quite simple. To begin, we declare two variables, x and a, setting the stage for our calculations. For the rectangle's area, we raise a to the 6th power, considering a as the width and a raised to the 5th power as the height. Next, we delve into the heart of the problem, calculating the integral in the given interval. This integral provides an expression to determine the area of the bounded figure. The area of the figure we are looking for will be the area of the triangle, and this is half the area of the rectangle minus the area bound by the function. Our calculations reveal that the ratio of the area of the searched figure to the area of the rectangle is 1/3. In conclusion, this journey with SimPy has allowed us to explore the fascinating world of derivatives, integrals, equations, and inequalities. I hope you've enjoyed this video and found it both engaging and informative. If you have any questions or thoughts, feel free to leave a comment below. Thank you for joining us on this adventure and watching until the end.